Welcome to the deep dive. Today, we're tackling a really interesting question that actually came from you, our listener.
That's right.
How well do AI models actually know when they don't know something?
Yeah, it's a fundamental question.
We've got some research here comparing two specific models, let's call them Model A and Model B, looking right at their ability to spot what are called undefined samples.
Things they haven't seen before, basically. Stuff they weren't explicitly trained on.
Exactly. Like, can they recognize newness?
It's all about that recognition.
Yeah.
Imagine you train an AI on, I don't know, just cats and dogs.
Yeah.
Then you show it a hamster.
Right. Does it go, whoa, what's this? Or does it
Yeah.
just try and force it into cat or dog?
Precisely. And this research you sent over, it sets up a specific way to judge this. A sample is considered recognized only if at least 6 out of 9 internal bits of the model agree on the same label.
Okay, 6 out of 9 agree.
And their average confidence has to be high, over 90%.
Got it. So our mission today is really to dig into what happens when those conditions aren't met. How do Model A and Model B stack up based on this data?
Let's dive in.
Okay, so maybe let's start with a failure case. The research mentions this elephant example.
Ah, yes, the elephant.
Yeah.
So picture this. A model trained on various animals, but maybe the only hoofed animal it really knows well is a horse.
Okay.
You show it an elephant, what happens? Well, in this particular test, both Model A and Model B looked at the elephant and said, horse.
Oh, okay. Not great.
No. And it highlights a key limitation. If the training data only provides one sort of vaguely similar category,
Then unknown things can just get crammed into it.
exactly, they don't have the mechanism to say, hang on, this is something else entirely. Neither model flagged the elephant as unknown here.
So for someone trying to get a quick grasp on AI limits, this shows that even complex systems can have these blind spots.
Definitely. But then things get a bit more nuanced.
How so?
Well, you might think, okay, just train the model on more things. More classes should be better, right?
Seems logical, yeah.
But test set 2 in this research showed something counterintuitive. Sometimes having more classes can actually make it less sensitive to unknowns if there isn't a really close match.
Huh. Okay, explain that. Test set 2 involved a misclassified horse.
Right. So both models initially looked at this specific sample and said horse, which, okay, makes, in a way, it was a horse, just one that maybe confused the models a bit.
But the difference was in the confidence.
Exactly. Model A, its confidence was only about 85.2%.
So below that 90% threshold we talked about.
Precisely. So because it wasn't sure enough, Model A flagged it as undefined. It basically said, I think it's a horse, but I'm really not certain.
Whereas Model B,
Model B was more confident. Too confident, actually. It confidently misclassified it as a standard horse. Didn't flag it as anything unusual.
okay, so Model A's uncertainty was actually a good thing there. It acted as a warning sign.
That's a great way to put it. It shows that sometimes, paradoxically, having fewer trained categories, or perhaps less specific training in some areas.
Can make the model better at spotting when something just doesn't fit.
Yes, it's like the boundaries are a bit looser, allowing it to recognize things further outside its core knowledge. It's not just about cramming more and more data in.
So looking across all the tests they ran, all 3 test sets,
Yeah.
what was the overall picture?
Pretty clear, actually. Model A consistently did a better job detecting these undefined samples.
By how much?
On average, Model A got it right about 77.8% of the time. Let's say roughly
Like
78%.
Model B?
Way lower, only around 44.4%, so like 44%.
That's a significant difference.
Huge. And it was really rare for Model B to do better. Only happened in 1 out of 90 samples tested across the board.
Okay, so the big takeaway seems to be what? Fewer categories can help. Sort of. It suggests that fewer training categories can sometimes lead to these looser boundaries, which, kind of surprisingly, helps the model identify genuinely unfamiliar inputs more effectively.
And Model A was just better at that overall.
Yep.
Better at knowing what it didn't know.
In most scenarios presented here, yes. And that ability to say, I don't know, or at least flag uncertainty, is really important.
Absolutely. Especially when you think about using these AI systems in the real world, right?
Right.
Where they will encounter unexpected things.
For sure. Model A's tendency towards caution, you could say, looks like a real advantage there.
And for our listener, aiming for that quick but deep understanding, this really highlights a crucial bit of AI performance. It's not just about accuracy on known stuff.
It's also about understanding the limits of that knowledge. How well does it handle the unknown?
Right. So considering all this, the risk of forcing unknowns into the wrong boxes, The fact that more data isn't always the answer for detecting novelty. It makes you think.
It does. What are the real-world implications when we deploy AI in situations where, you know, encountering totally new data is pretty likely? What kind of safeguards or maybe different strategies do we need to think about?
That's the million-dollar question, isn't it? Definitely something to mull over.